second part,
Recording
we'll be talking about specific monoids inside a category. So as we saw before that there are some monoids that are more interesting than others and that are easier to study. So here there will be two directions. The first direction is if I start with a monoid A, then I could get from this monoid a simple semigroup S, which I will define everything later, of course. And from the simple semigroup, I can construct a category with two objects such that one of the objects is a group. And the second direction is just the opposite. If I have a category with two objects and one of them is a group, then I could get a simple semigroup and I could extend it to a monoid. And in this section, I will be writing the matrix of a category in a little bit different way. And then if I fix two monoids, A and B, and I let a category with two objects, X and Y, such that the first monoid between X and X is A, the one I chose here. And between X and Y, we name it L. Between Y and X, we name it R, and between Y and Y, we chose the other monoid B. Then the matrix to this category will be ALRB, and we will call it algebraic matrix of C. And the difference between this matrix and the other matrix where we had numbers is that in this matrix, the monoids are fixed. So A and B are fixed. We know exactly the structure of these monoids. So as we said before, we fix them like C1 or C2. We know what we have here, and this will surely affect the structure of L and R also as well. And first, I will start with categories where one of the endomorphism monoids is a group. So if I have a category C associated to this matrix A, L, R, and G, where L and R are not empty, and it's always the case. We're always treating the case where they are not empty. And G is a group of order n. Then if we have a group, it acts on L and R, we have a group action, and G acts actually freely on L and R. And just to remind you of the definition of free action, it is when the stabilizer group of each element in L and R is only the trivial group. It means that if we have X in L and G in G, so Gx or Xg equals to X, it means that G has to be identity. So only the identity fixes the elements of L and R, and it's called the stabilizer group. And we obtain, because of this free action on L and R, we obtain that the cardinal of L and R should be multiples of G when we have of the order of G, when we have G as monoid. And the reason goes actually to the orbit stabilizer theorem, because the cardinal, if we take any element in L, the cardinal of this element X, it's going to be, by the orbit stabilizer theorem, it's going to be the order of the group over the order of the stabilizer group. And because the stabilizer group is just one, so it's equal to the order of the group. Then I have a bunch of elements in L that have orbits of size order of G. So the whole L will be multiple of order of G, and the same for R. And as a corollary, if G acts freely on L and R, then it will act freely on L plus R. And then if I define the set L tensor R to be L plus R quotient by the equivalence relation of the group, then there will be a map from L plus R to LR, to L times R, which is going through this set L tensor R. And actually the main reason I want to do that is I want to know, because I have a matrix, and I know that L times R is inside of A, and I know that R times L is inside of G. So I need information about these two multiplications. So I need to know, I know the conditions on the size of L and size of R. So I need to know the conditions on the size of L times R. And I let C a category associated to this matrix, A, L, R, and G. And I consider the quotient, this one that we defined before. And the function from this quotient to LR, defined by xy, is going to be bijective. And this, what does this mean? It means that the cardinal of this set is going to be equal to the cardinal of this set. So the cardinal of LR is equal to this, and by the free action, it's actually equal to cardinal of L, cardinal of R over order of G. So I know now that I have, as a conclusion of this section, if I have G as object, as monoids, L and R are multiples of G, and LR, the multiplication LR into A, is equal to LR over G. I know the cardinality of all of these sets, and which makes A, the cardinal of A should be greater or equal than this. And now I will start the first part of the first direction, or a part of the first direction is that if I have a simple semigroup, how do I get to a category with two objects? So first, a semigroup S is simple if its only ideal is itself S. And I get this theorem if I have a simple semigroup S and I take a minimal left ideal of S and a minimal right ideal of S, L and R. So first we need to forget everything before. We have now a semigroup. We're starting with semigroup. We don't have a category, and we're building the category. And L and R are minimal left and right ideals of S. So the multiplication LR is going to be equal to the semigroup itself, because actually LR is a two-sided ideal, and we said that S is simple, so the only ideal is S, so it's going to be equal to S. And the intersection of L and R will be a group that we will call it G. And also the intersection is going to be equal to RL. Normally it's not the case. Normally there is an inclusion, but we have equality here because L inter R is actually a group. This is the case. This is the reason. And I want to say a remark also here that there is something called a zero simple semigroup, and it is when A has a zero and the only ideals are S and zero. And now it's a much more complicated case. So in our work here, we're only considering that A does not have a zero, and it's just a simple semigroup, not a zero simple semigroup. So a theorem: if I have a simple semigroup and I have L and R minimal left and right ideals of S, then I can construct a category C associated to this matrix, S star 1, L, R, and G, where S star 1 is S union an identity. And we actually add formally an identity to S because S is a semigroup. And as we said before, semigroups do not have neutral elements. So we need an identity in order to become a category. So we just add formally an identity. And I know that RL is equal to G by the previous theorem, and I know that LR is equal to S by the previous theorem, and all of these restriction on the cardinality of sets. So L and R are multiples of order of G, and the cardinal of S, which is equal to LR, is equal to LR over G by the first section about groups. So this is how we obtain a category of two objects if we start with a simple semigroup. And actually the construction of this category is not very obvious, but we will also not go into details, but we use something called Karoubi envelope construction. which is basically taking the idempotent elements of S. And here we take only two idempotents, which one of them is going to be the identity of S, and the other will be the identity of G. And we just multiply the left ideal by the first idempotent on the left and the second idempotent on the right, and the same for R. But this is like just an idea of how we do the construction. So we want to know, to start actually with a monoid and not just a simple semigroup. So if we start with the monoid, how do we get to categories? If I have a finite monoid, A, then A has a unique non-empty minimal ideal, which will be denoted by S0. So every finite monoid has a unique non-empty minimal ideal, which is actually the intersection of all minimal ideals. And again, if we have 0, then the intersection will be 0. This is why it will cause so many problems if the intersection is 0. And S0, the minimal ideal of A, is actually a subsemigroup of A, and it is not any subsemigroup. It's going to be a simple semigroup of A, because it's minimal ideal, so it doesn't have any other ideals except itself, so it is simple. This is the definition. And a very important lemma is that if I have a finite monoid A and its minimal ideal S0, then the minimal left ideals of A and the minimal right ideals of A are the same as the minimal left ideals of S0 and the minimal right ideals of S0. So A and its minimal ideal S0 share the same minimal left and right ideals, which is going to be very important in our construction. So a theorem, if I have a finite monoid that is not a group, the condition that A should not be a group, because this will lead us to have two groups on the diagonals, and I will also not go into details, but this will give us a groupoid instead, and some problems with the reduced property. So we don't consider the case that A is a group. So A is monoid, and S0 is its minimal ideal. So by previous section, because S0 is a simple ideal, I can construct a category from S0. I will call it C prime, such that S0, the category is associated to S01, L, R, and G. And again, one here is just I added an identity. And I have L and R are minimal left and right ideals of S0 because I just chose them. But because of the previous lemma, because L and R are not only minimal left and right ideals of S0, they're also minimal left and right ideals of A, then I can extend this category C prime to a category C associated with the matrix A, L, R, and G, such that C prime is going to be contained in C. So this is the first direction of that we want to prove is if I start with a finite monoid, I could obtain a simple semigroup, and from the simple semigroup I can construct a category associated to this matrix, and I have all the cardinality conditions that hold, and from this, because of the property of left and right ideals, minimal left and right ideals, I could extend it to this matrix. So this is how I construct a category with two objects out of a monoid. And now the other direction. So now if I have a finite category such that one of the objects is a group, how do I get to a simple semigroup or to a monoid? So I let C be a finite category associated to the matrix A, U, V, G. I will call them U and V for now, but we will see later how does it work. And G is a group. Then the multiplication UV, which goes into A, is going to be a simple ideal, and such that the cardinality, we will call it S, the cardinality of this simple ideal satisfies this. And because it's a simple semigroup, as here we can construct a subcategory of C associated to the matrix S star 1 UVG. Because I could see that UV is actually the image of the multiplication in A. It's like a function from E to F, and FE is inside F, so it's the same. So it's UV is the image and it's inside of A. And this tells us actually that if I have a group in here, all the multiplication of elements in U and V will go only to the simple ideal of A, which is like the interesting part. And we will explain a little bit how we do the construction. So if I have a finite category associated with this matrix, I and G is a group, I take X in U and Y and V, and I define Ly to be the set U times Y, which is an element in V, so it's inside of A. And I also defined Rx to be X, which is in U times V, the set V, which is also going to be an element, a subset of A. And it's clear that we want to prove that Ly is going to be a minimal left ideal of A, and Rx is a minimal right ideal of A. And why we want that? Because when we start with the monoid, the category that we obtain, the sets of morphisms are the minimal left ideals of A and the minimal right ideal of A. But here, we don't know anything about U and V, so we want to know how do we get to a category where we have minimal left and right ideals of A on these off diagonals. And for remark, if I replace Y by GY, it's going to be the same. So it's we can replace Y by GY. It's also the same for V. We can replace X by XG. And the proposition is, so yeah, now I want to show how do I get the minimal left and right ideals of A out of this matrix. So I take the set of minimal left ideals of A, LA, and the set RA, the set of minimal right ideals of A. And then I define the set V quotient G, which is all the sets like XV, and by the group equivalence relation, and U quotient G, which is going to be UY. And I prove that this set is equals to LA and this set is equals to the set RA. And what does that mean? It means that for every minimal left ideal L and A of A, which is in LA, there exists Y and V such that L is equals to Ly. And for every minimal right ideal R of A, there exists X in U such that R is equals to Rx. And this is how I associate morphisms in a category to their set of minimal left and right ideals of A. Then I have this lemma. If I have a category associated to this matrix, where G is a group, then as I said, UV is a simple ideal of A. And actually, if I make a choice for every XY, YX is the identity in G, then I can prove that the multiplication of L, Y, Rx is actually going to be the multiplication of UV, which is the simple ideal. So the multiplication of the minimal left ideal and the minimal right ideal is equal to S, the simple ideal, as we proved in the previous sections. And we denote GXY by RX LY. So this is the group that is obtained by RX and LY. And the theorem is, if I have a finite category associated with this matrix, then I get a a simple semigroup, which is the UV or LY or RX. But because I have a simple semigroup and I have a monoid that has a simple semigroup and left ideals and minimal ideals that are like this, LY and RX, obtained by U and V, I could construct a category C prime associated to this matrix A, LY, RX, GXY. And this is all in the section where we start with a monoid to a category but this time I constructed the left minimal ideals and the right minimal ideals out of U and V. And I know that the multiplication of L and R is S, the simple ideal of A. And this is the group GXY. And the result of this theorem is actually this category C prime is going to be isomorphic to C. So both categories are isomorphic. So it's the same when we construct the left minimal ideals and right minimal ideals of A. It's the same as staying in the same sets of morphisms, and the category obtained is unique. As a conclusion, what we want to know is if I have a category associated to this matrix, and under the choice of X and Y, I can obtain a subcategory C prime, and not actually a subcategory, a category C prime that is unique, associated to A, LY, or X, GXY, and these two categories are isomorphic, and the coefficients in the matrix satisfy these conditions, and it means that we get that A should be greater or equal than UV over G plus 1. And actually, if we reformulate this formula here, this inequality, we obtain that the determinant of the matrix M should be greater or equal than the order of G, which, if you remember in the first section, when we had a matrix A, B, C, D, we said that if one of the diagonals is 1, then the determinant should be greater or equal than 1. And here it's the same, but we have a group G because 1 is just a particular case, it's the trivial group. But it's harder to see, it's much harder to see when we have 1 because UV are going to be multiple of 1, which is always the case. So this is a generalization of the case where we have 1 on the diagonal, the trivial group. And finally, in the last section, I will talk about connectivity of monoids. I recall that two monoids are A and B are connected if there exists a category with two objects such that its endomorphism monoids are A and B. And we say that a monoid A has a group G if its minimal ideal is connected to G. So from the previous sections, it's just that if I have a monoid and I have the simple ideal, G is the group obtained by the minimal left and right ideals from everything before. And from also everything before, we know that every finite monoid A, there's always a group connected to A, and it is through the minimal ideal S of A, as shown before. And a lemma by Jeremy Marquez, it says that if AB are connected and BC are connected, then AC are connected. So it means that the connectivity property is transitive. And from this lemma and by our work before, we conclude this theorem that two monoids are connected if and only if they have the same group. So if they share the same group. This is actually a full classification of categories with two objects where one of the objects is a group. The other monoid should contain a simple semigroup with the cardinality that we showed, and all the multiplication goes into the simple semigroup only. It doesn't go out of the simple semigroup. And this is all. Thank you.
Thank you very much, Najwa.